Assalamualaikum and hi. My name is Nurul Syazwani binti Muhammad Shahrizal. My matrix number is 223284 and I will presenting fluid features and dimensional analysis concept. Before I start, I would like to highlight the objective of my presentation. The objective of my presentation is to explain about fluid features and to explain about dimensional analysis concept. Firstly, what is fluid mechanics? Basically, fluid mechanics is the branch of physics and engineering that deals with the behavior of fluids, which is liquid, gases, and plasmas at rest, which is known as fluid statics, or in motion, fluid dynamics. It is a fundamental discipline that studies how fluids behave under various conditions and how they interact with their surroundings. This is the list of the fluid features that I will present. It is density, viscosity, compressibility, pressure, temperature, surface tension, and specific heat capacity. First, I will start with density. Density is a fundamental property of fluids that describes how much mass is packed into a given volume. It plays a crucial role in understanding and predicting the behavior of fluids in the various applications across science and engineering. Density is defined as the mass of a substance per unit volume, which is known as ρ equal to m over v. In the International System of Units, SI unit, density is typically expressed in kilograms per cubic meter. In other systems, it may be expressed in gram per cubic centimeter or pound per cubic foot. Next is viscosity. Viscosity is a fundamental property of fluids that describes their resistance to flow. It influences how fluids move and behave under various conditions, making it is a critical parameter in fields such as fluid mechanics, chemical engineering, and material science. Viscosity is the internal frictional resistance of fluid to motion. It is defined as the ratio of shear stress to the rate of deformation, and the equation is viscosity shown in the slide. In the SI system, viscosity is typically measured in Pascal seconds, or equivalently in kilogram per meter per second. In the CGS, which is known as centimeter gram second system, it also measured in poise or centipoise, where 1 centipoise equal to 0.001 Pascal second. Next is compressibility. Compressibility is a property of fluids that describes the extent to which their volume changes under pressure. It is a critical parameter in fluid dynamics and thermodynamics, affecting the behavior of fluid under varying conditions of pressure and temperature. Compressibility is defined as the relative change in volume of a fluid when subjected to a change in pressure, and the equation is compressibility is shown in the slide. Next is pressure. Pressure is a fundamental concept in physics and fluid mechanics that play a critical role in describing the behavior of fluids and their interactions with solids and gases. Pressure is defined as the force exerted per unit area. The equation for pressure is P equal to F over A. In the International System of Units, SI unit, pressure is measured in pascals, where 1 Pascal equal to 1 N over M. Other common units include atmosphere, pounds per square inch, and millimeters of mercury. Next is temperature. Temperature is a fundamental physical quantity that quantifies the degree of hotness or coldness of an object or a substance. It is a key parameter in various scientific disciplines, influencing the behavior of materials, chemical reactions, and physical processes. Temperature also is a measure of the average kinetic energy of particles in substance. In simpler terms, it indicates how fast the particles are moving within material. The scales that usually used is Celsius, Fahrenheit, and Kelvin. And converting between these scales is done using specific conversion formulas to account for the different 0 points and interval between degrees and on each scale. Next is surface tension. Surface tension is a fascinating phenomenon in physics that describes the cohesive forces acting on the interface between a liquid and a gas or another liquid. It is a result of intermolecular forces between molecules within the liquid, creating a kind of skin or film on the surface that resists external force. Surface tension is defined as the force per unit length acting at the surface of a liquid in contact with air or another medium. It is measured in units of force per unit length. For molecular basis, surface tension arises from cohesive forces between molecules within the liquid, particularly at the surface where there are fewer neighboring molecules to interact with. This results in an inward cohesive force that minimizes the surface area and tends to pull adjacent molecules closer together. Next is specific heat capacity. Specific heat capacity is the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Specific heat capacity determines the amount of energy required to change the temperature of a fluid. Features involving heat transfer calculations, like thermal management systems, energy storage, that require knowledge of this property. Now I will continue with dimensional analysis concept, which is about fundamental and derived units, dimensional homogeneity, dimensional analysis steps, and the application. Firstly is the fundamental and derived unit. Fundamental units are basic units like meters for length, kilogram for mass, second for time, while derived units are a combination of fundamental units such as velocity, acceleration, and force. The table below shows the fundamental unit and derived unit. Next is dimensional homogeneity. This principle states that in a valid physical equation, all terms must have the same dimensions. For example, in the equation F equal to ma, which is Newton's second law, both sides must have dimension of force. Next is dimensional analysis steps. First, assign dimension, such as L for length, M for mass, T for time to each variable. Second is formulation equation, which is express relationships between variables using their dimensional forms. And next is checking the consistency to ensure all terms on both sides of an equation have the same dimension. Next is the application. Firstly, we need to check the equation. Dimensional analysis can identify errors in equations by revealing inconsistencies or in units. Next is predicting relationships. It can predict how variables are related when the exact equation is unknown but the dimensional form is known. Next is scaling laws. It helps derive scaling laws in physics, such as how certain physical quantities change the scale. Lastly is the conclusion. Dimensional analysis is particularly valuable in fluid dynamics because it allows us to understand and predict the behavior of fluid without needing detailed knowledge of their specific properties. By focusing on the fundamental dimensions, such as length, mass, and time, dimensional analysis help us derive dimensionless number, like Raynaud number, Mach number, that characterize fluid flow phenomena. This dimensionless number reveal how different forces and influence the flow patterns and behaviors of fluids across various scales. In essence, Dimensional analysis simplifies the complexity of fluid dynamics by highlighting the essential relationship and scaling laws that govern fluid flow.